Let's have a look at this dynamics problem, which involves a 20 kilogram box that's sliding down an incline. So let's label all the forces that we know. So this one is force due to gravity. This one is force due to the effort. This is our normal force, and this is our frictional force. So let's work out what our force due to gravity is. So force due to gravity is equal to mass times gravity, which is equal to 20 kilograms times 9.8, which is 196 newtons. So if we think about that, let's draw our box here. So we have on the downward angle, this is our force due to gravity. We have 196 newtons. All right. Now, going in this direction, let me get the angle right. This is our normal force. Okay, so this is the force that the slope or incline exerts back on the box, and we're not too sure what that is. And on the other hand, we have our frictional force, or we have this is our force due to the effort. Okay. So let's determine what is the force due to the effort of this block. And we know that the angle inside here is 21 degrees. So the sine of 21 degrees is equal to force effort over the hypotenuse, which is 196 newtons. So our force due to effort is equal to 196 newtons times the sine 21 degrees, which is 70.24 newtons. So this box sliding down the slope is sliding down with a force of 70.24 newtons. Now if we want to know the acceleration of this box as it goes down the slope, it's not equal to gravity because it's not directly going vertically down. It's actually partially on a slope. So if you think about it, this vector here, right? So our force vector, let's redraw that. So our 21 degree slope is actually partially this, which is gravity, and partially this. So as you can see, the gravity portion of it is actually not the full 9.8, so it's a portion of that. So let's look at that now. So let's look back at our problem. We have, so force due to the effort is equal to mass times acceleration. So if we go 70.24 newtons is equal to 20 kilograms times acceleration. So our acceleration going down the slope is equal to 70.24 newtons over 20 which is equal to 3.51 meters per second squared. So that's the acceleration that this box is going to be going down the slope. Let's have a look now at a few sample problems. What if I wanted to know, for example, so let's rewrite it up here. So the acceleration is equal to 3.51 meters per second squared. And let's imagine that this box here is actually 2 meters above the ground is where it starts, the starting point. So what would the velocity be at, let's call this point B and this is point A, at B. So what would it be if it reached the end of the slope? Let's have a look at that. So we know that potential energy is equal to mass times gravity times height, which is equal to 20 times 9.8 times 2 meters. So that's 392 joules. Now, let's look at the fact that potential energy plus kinetic energy initial must be equal to potential energy plus kinetic energy final. So this is at A and this is at B. So at A, it's at the very top. So we have no kinetic energy. And at B, we're at the very bottom, so we have no potential energy. So the two must be the same. So therefore we could say 392 joules is equal to 1/2 mv squared. So that's the formula for kinetic energy. We can rearrange that, so we get 2 times 392 joules divided by the mass, which is 20 kilograms, is equal to velocity squared. So the velocity is equal to 2 times 392 over 20. So we get a velocity of 6.26 meters per second, and that's at point B, at the very end. How about if I wanted to know how long did it take to get from point A to point B? Let's have a look at that problem. How about time to get from A to B? So let's look back at our formulas. What formula could we use now? Let's have a look. Let's see if I can delete that. Okay. So we would need to consider the different states. So we could utilize this. So let's plug that back in. Acceleration is equal to final velocity, take initial velocity over time. We know final acceleration, we know acceleration, and we know final velocity. So we can plug that in. So let's rearrange. Time is equal to velocity, take initial velocity over A. So we have 6.26 meters per second, take initial velocity of 0, divided by our acceleration, which was 3.51 meters per second squared. So if we divide that, it takes 1.78 seconds to reach the bottom. So that's just a couple of ways to think about these type of problems.